Yep, I think we're ready to go. So, good evening, everyone. Thank you for joining us on our webinar this evening titled HV Distribution Networks. I am Ghada, I am a member of the IT East London Network, and this is our first webinar for 2020. We have an amazing turnout tonight, so thank you, everyone. Our speaker today is Nick Thompson, who is the HV Training and Marketing Manager at Schneider. Nick joined Schneider's Power Systems Marketing Department back in 2004, and since joining, he's managed various types of switchgear, transformers, and protection relays used in HV networks. In the past 6 years, Nick has focused on HV equipment training. But before I hand over to Nick, I'd just like to remind everyone to please think about some questions during the discussion and post them using the Q&A function. It can be found at the bottom of your screen. Also, please use the comments box if you have any other comments or queries. Well, without further ado, over to you, Nick.
Right, thank you very much indeed, Garda, and good evening, everybody else. As introduced, my name is Nick Thompson, and I'm with Schneider Electric. And tonight's presentation is about HV distribution systems. Now, I know it is billed as MV, but in the UK, and I don't know if there's anybody from outside the UK joining this, we have a set of regulations which cover wiring, and it's known as the 18th edition. Now, in the 18th edition, it states two voltages or voltage bands. One of them is low voltage, up to 1,000 volts AC, and the other one is high voltage, above 1,000 volts AC. So hence the change from MV to HV, but other countries may have different practices. And in fact, there is an IC standard which does actually detail the various different voltage bands, going right up to ultra high voltage. In the industry that I'm from, the electrical engineering industry, globally, we refer to medium voltage as a voltage band from 1 kV up to 40 kV, and it helps kind of define the switchgear, because the higher the voltage, the change of switchgear certainly gets a heck of a lot bigger. So like Garda has already introduced me, Nick Thompson, I'm representing Schneider Electric, have been there since 2004. A lot of the information I'm going to pass over to you today is what I use in one of my training courses within Schneider. You'll notice there it is also CPD certified as well. And I believe you can download the appropriate certificate from the website, but Garda will be able to advise you more on that. So without any further ado, let's kick off. So if the system will work. Okay, these are the subjects I'm covering in tonight. So we're going to look at what a network is and go into the various different networks. So radial, open ring, closed ring. And then I've got a few customer examples of various different networks that I've come across over the past 4 to 5 years when I've been looking at concentrating on training. And then there's one specific thing I want to touch on tonight is about generator connections as well, which can be quite important as far as your connection is concerned. But more on that when we get to that slide. So when we start to look at networks, everybody gets a little bit scared about the term high voltage. In fact, distributing high voltage is no different to distributing LV. In fact, LV, you've got a right myriad of different types of connections, different devices, etc. And this is a typical UK domestic or even a commercial office kind of ring. So we've got the consumer unit with the relevant MCBs, different sizes. We've got cables that are buried underneath the floor, or for lighting circuits that are in the ceiling, and then we've got the sockets at the appropriate height, depending on the age of the property and as to which regulations it was wired in. So we end up at the final point being used. In this case, I've got the example of a kettle. It could be a pair of tongs for straightening hair, or your mobile phone charger, or whatever. It doesn't matter. The end point there is the final consumer. Cables are cables, whether they are copper or aluminium. Typically in domestic, it's aluminium, it's copper, but in HV, it could either be copper or aluminium, depending on the standard specification, etc. Now, when we look at a HV network, we've still got the same kind of scenario. We've got our circuit breakers, but this time with HVs or medium voltage circuit breakers, they are much bigger. They make a heck of a lot more noise due to the springs that are driving the circuit breakers open or closed, depending on what you're doing with it. The cables are going to be constructed in a completely different way to LV cables, and your connection there, you've got typically it's a ring main unit. Now, a ring main unit sits on a ring, hence the term ring main unit. And ultimately, we got to the end point there. We're going to step down from the HV, in this case, it's 11 kV, into the transformer, and then you're going to step down to more manageable for a commercial or domestic application, i.e. the transformer. Now, the cables will be routed wherever it's practical to go. So you'll find cables running underneath the pavement outside your own home, outside the office. You may even have, if you're HV cables, routed inside a large complex. So it's like oil and gas, or data center, or even hospitals will have their own HV networks. And that's typically why we need to look at the different types of networks, which are principally going to be used in distributing HV in private applications. The DNOs have got their own strategies for distributing power around their network. And remember, the DNOs are licensed for managing. They're not licensed to sell. This is distribution network operators in the UK. Outside of the UK, they'll be termed as utilities, ESB in Southern Ireland, for instance, and then France and Germany, etc. Depending on the country, it will depend as to different utilities. So France principally has just got the one utility. Germany have got more than that, and most utilities, or all utilities, will be regulated by a government office or local government. So it may be central government, then spreads out to regional governments as well. But in the UK, the regulator is Ofgem, and they license the individual network operators to manage that network. And this is just a very simple explanation as to the different types of networks that could be seen in 11 kV public distribution. So it comes off the grid, from the national grid. If it's in England, in Scotland, it will be SSE or SPEN, Scottish Power. In Southern Ireland, it will be Airgrid. So we step down from on the national grid, it's 400 or 275 down to 132 kV, and then down to ultimately here 11 kV. And we've got our primary distribution board, which is this large switchboard here, which will have multiple feeders at different current ratings, with typically going to be 2000 amp incomers with a 2000 amp bus section. And then we've got a ring showing there, and this will be a co-ownership switchboard. And then they've got their own feeders there. Radials, maybe a mix of radials, maybe a mix of open ring or even closed ring, depends on the site and the supply requirements. Here, this is two radials in parallel coming into this particular site here. So this will be wholly owned by the site operator or owner. The incomers may actually be owned and operated by the local DNO. Depends on the arrangement. And then we've got the rural, and when you see the overhead lines that are scattered around a lot of countries, the UK is no different. We have a lot of wooden overhead lines, wooden poles, typically for the UK. And that's typically going to be 11 kV or 33 kV. It will depend as to where you are in the country as to what voltage it's going to be. It's easily identifiable in the UK as to what voltage it's being configured for, is by counting the insulator rings on the end of each line connecting onto the poles. If it's 2, it's typically going to be 11 kV. If it's 4, it's going to be more than likely 33 kV. However, moving on. So let's have a first look at a radial network. So a radial network typically is going from the supply circuit breaker, which is this one here, through to an endpoint. And quite often you would find a radial network with just a piece of cable, depending on however long it's going to be, going from the circuit breaker to a circuit breaker, and then maybe a transformer or a switchboard, depends on the site. So the site where I'm based at, which is in Leeds, we are fed from the DNO ring on a radial to our own HV switchboard, which comprises of one incoming circuit breaker and then 2 transformer feeders. And the transformer feeders are cable connected, so they're going to be radials. But in this instance here, I'm showing 3 substations. Now, I have come across this kind of network in a customer's application, and it's because of the site construction where it dictated they could only use radials with numerous substations on those radials, and they accepted the operational sort of limitations that you have with this kind of network, which if we introduce a fault now on our network at some point, be it short between phases inside the cable, or actually the cable getting chopped through from the JCB, which they are very, very good cable finders. You're going to get a short, and that's going to be face to earth or face to face, whatever. Either way, you're going to get a potentially serious situation where if the circuit breaker doesn't trip because of the fault, then you could ultimately have problems on that part of the network. But hopefully, if everything's working okay, the circuit breaker will trip, and then that's isolated the fault. And then, unfortunately, we've lost all 3 substations. So A, B, and C have actually gone out. Now, under these circumstances here, you would then normally have to identify where the fault is. Now, it could be quite easy to find where the fault is. You've got a hole in the ground, or the JCB with a bucket with a piece of cable stuck on the end of it. That's easy to find, but sometimes it's not that easy to find where the fault is, particularly if there's no evidence. Now, if we know where the fault is, it's going to be easy, and we can do something about restoring supply to one of the substations, which happens to be A. So once we know where the fault is, we can work out what the switching schedule is going to be safely. Now, that switching schedule will be written by an authorized person, probably signed off by a senior authorized person, and then the switching would then commence. So here we've isolated the faulty piece on the left-hand side. So substation A, right-hand side, right-hand ring switch is now open or off. And in most ring main units, the switch is also rated to be a disconnector as well. So it's got a much larger gap inside the tank. Now, that operationally will allow us to safely close the circuit breaker and then put customers back on supply. Post interruption, obviously, you would need to do some checks on the equipment, particularly on the feed circuit breaker, to make sure everything is healthy and safe to close. Also, the substation that's directly above it, the fault, would also probably need to be checked to make sure there's no resultant damage to the equipment with the high fault current which is flowed through, because the switchgear may have been subjected to previous high fault currents and may have created some damage. So there's going to be post-fault checks that would need to be done before and re-energizing the system. And then the cable could then be repaired leisure is not the correct word, at the appropriate time to get B and C back on supply. It may be that the whoever's off is creating a right stink and putting pressure on whoever is going to repair it in a timely manner. Ultimately, if you can't get repaired quickly, then backup generators may have to be brought in to re-energize the affected sites. So that's one of the problems with the radial network, and but you can get people back on just by doing some simple switching and isolation of the fault. Now that will lead me on to an open ring, because an open ring, as it says on the tin, we have this open point over here. So when I get my pen, we get this is an open point. This is a deliberate break in the network. So we're effectively creating two radials. Radial from here and a radial here. So it is, as it says there, it is two radials, commonly known as an open ring. Now, this is the most typical network you will find operationally, not only with utilities, but also in private networks as well. It's simple to install, simple to operate, and it is also the most cost-effective when we compare against the next network, which will be a closed ring. Now, I'm going to introduce a fault, and we can actually see what will happen just by my simple graphics. So we've got the fault there, and we get fault current like we did on a radial to the point of the fault, and that's as far as it's going to go. Now, when you get a fault on any network, you're going to get voltage. The voltage will dip. It's the natural physics. So the volts drop, the lights will dim, and then maybe recover if it's on an unaffected part of the network. So on here, A, B, and C might not see a drop in volts, so they may not know what's going on, but E, D, and F will notice what's going on because the circuit breaker will trip. Now, one thing I'd like to point out at this point here, your equipment that is on that network has got to be capable of withstanding the high fault current that's going to flow through each closed switch and possibly the closed circuit breaker for a short period of time. Now, that's called current withstand, and all switchgear manufacturers will design the switchgear and have it tested independently in a laboratory, and there will be then test reports will be issued to say that yes, it passes the test. Now, each country is going to have its own time for testing on, or for time withstand of those devices, and in the UK it's 3 seconds time duration. Other countries are going to be different, and it's the time duration is totally different to another fault issue, which is going to be internal arc, but that's not for discussion tonight. So all these switches and circuit breakers that we've got in the path of the fault have now got to withstand that fault current for that period of time. Now, hopefully, the fault is not going to be there for that long, but the reason it's for three seconds is to allow the circuit breaker chains, and this is not the immediate one. This is this one up here. It's maybe the one above it, and maybe the one above that. If this one doesn't trip, for whatever reason it is, and it could be through the circuit breakers jammed, the protection relays faulty, or whatever. So you're relying on the next one up to actually do the work. So hence that's why we have that time delay there, so that length of time. So now we've tripped, and we've lost supply to our 3 substations. Now again, provided we know where the fault is, we can do something about it fairly rapidly. So in this case, it's between E and D. So by working out where the fault is, not necessarily exactly where the fault is, we just need to know it's between substations. In this case, we can now start to work out a switching schedule to restore supply to all substations. Now, under this network here, you've got to take into account you're going to have time delays. Now, those time delays are going to run from literally minutes, maybe hours, but it depends on the site and the operational requirements. So we know where it is. So we've worked out our switching schedule. So this is just my sort of thoughts on this. In reality, it may be something slightly different, but we've got the left-hand ring switch on substation D is now open. We can now safely close the right-hand ring switch on substation D. That's restored supply back to that transformer. Moving into substation E, we can then open the right-hand ring switch. That's now isolated it at both sides. Remember, our ring switches are rated for a disconnector, so they've got a much bigger gap, which will, in modern equipment, is going to give you a 95 kV impulse level withstand. So it's not likely to arc over inside the tank. If it did, then there would be something really seriously wrong with the equipment. And now we can go back to the main intake substation and close the circuit breaker. Everybody is now back on. Happy days. But what happens if you don't know where the fault is? Well, is there anything that you could actually use to aid that identification? And we're not bothered about pinpointing exactly where the fault is. We just want to pinpoint between substations. And one of the very simple devices that we use is earth fault passage indicators. And these are a very simple device which basically strap onto the leg of the ring main unit, and this is typical for the UK. So they're external to the protection. It doesn't rely on the protection of the ring main unit. And as it says on there, if you repeatedly re-energize a faulty part of the network, you are constantly re-stressing the affected area. And when we mean by re-stressing, you're stressing all the components in that faulty area, the cables, the switchgear, and more importantly, your feed circuit breaker. When you start to look at feed circuit breakers, you've got to take into account the life of the circuit breaker, and that's not the design life. We're talking about in its operational life, not the mechanical endurance of it. We're talking about the number of full fault interruptions it's capable of doing. So if it's an existing site that's been there for over 30 years, maybe 40 years, and the HV circuit breakers have not been changed from the original installation, which possibly could be oil, you're looking at a maximum of 3 full fault interruptions before you need to maintain or replace the contacts. Well, you might have already had 2, and then you're on your 3rd with re-energizing, it trips again. So therefore, you're potentially going to exceed its capabilities, and it may have disastrous effects on the mechanism or the contacts or even the whole circuit breaker. So that's something to bear in mind. So these devices here, when we look at them, very, very simple. They do have an LED. You can test them. It will have a battery inside it, and the fault current that it's going to detect is down to the network operator and the commissioning engineer to actually set put the settings into here, and it's usually in the form of dip switches, very simple devices. And we do have a CT which is located inside the cable box. So that CT goes around all 3 cores, and it's commonly known as a core balance CT with the appropriate earth-in strap to allow the correct earth flow current. So the box will actually work out. Now, there are devices which can be incorporated into the LV box of the ring main unit, so it will sit alongside the protection relay. But when your equipment is going to be used outside, and you don't have authority to actually open up the switchgear, and you don't have the keys on the padlock, you need some sort of device to tell you, yes, a fault current has actually passed through me, and that's why the LED will flash. So in reality, this is the best way, is actually having a visible external device. You can actually wire these onto a light on the substation, for a visible indication. So you can drive past the substation without actually entering it. Now in the UK, some DNOs will actually specify how far up the leg these have got to be mounted. Quite often the DNOs will have these on a bulk contract, which will last for 3 to 5 years. And it's then they will, when they award the bulk contract, they will then tell the switchgear manufacturer which earth fault passage indicator needs to be engineered and fastened on to the ring main unit, and they'll say which side of which leg they want it to go on. So now we've installed earth fault passage indicators on our ring, and you generally only have one earth fault passage indicator on a ring switch. Sometimes the DNO will specify an earth fault passage indicator on both ring switches. So that depends on which way the network is configured. So this box here is our earth fault passage indicator. With its own CT, and that CT goes around all 3 cores. Introduce the fault again, and we get our fault current, which will pass to the point of the fault, passing through 2 earth fault passage indicators, ignoring the third because it can't go any further. The others, they're ignoring it as well because they don't have the fault current. Circuit breaker will trip. So as soon as the earth fault current passes through, there may actually be a short time delay built into the fault passage indicators, just in case it is just a blip. But once the circuit breaker is tripped, the LEDs will start to flash, and they will flash for a period of time because the onboard battery will only last for so long. So it'll be pre-programmed to flash for say 4 or 6 hours, after which it will then shut the LEDs down to preserve battery life. It could also be once we've restored the network, the earth fault passage indicators will then re-energize themselves. So if we're on our own private site, and some of these sites are going to be quite big, we will start at the substation. We know which network it is, and then we will just drive around our network. We'll visit each substation in turn, so we notice that's flashing, so we don't need to do anything there. We get to substation E, we notice that's flashing, and then we will continue on to substation D. That is not flashing, so we know our fault is now in between those 2 substations. So that could be readily identified quite quickly. If you're doing it manually, so you're driving around in a vehicle, or you're physically walking if the site's small enough, and it's basically following the breadcrumbs until the breadcrumbs no longer continue. Now, if you've got a very large site, you may need to consider the use of telecontrol, and this is SCADA. So it's a supervisory system which will monitor, and then you can, if you've got the authority, you can actually remotely operate your switchgear. Now, when you start to look at manual reconfiguration, that's obviously going to take a considerable time. And I've heard stories of private companies where time is of the essence. They didn't have the necessary remote monitoring, they couldn't identify where faults were, and they were losing complete batches of food production, which is obviously going to be very costly, but also you've got then you've got to take the time cleaning the whole system out before you can then restart the production. So SCADA or remote monitoring is a quick and easy way of identifying where your faults are, and then maybe working out what the switching schedule is going to be, and then ultimately then doing the switching remotely if you are allowed to do. Now, the photograph that I'm showing there on the right hand side is not a DNO, it's the National Grid from there, and I pulled this this image off of Google. So and that's the entire UK network. All the National Grid substations are unmanned, so therefore you've got to use very high-end SCADA systems to remotely monitor what's going on and then remotely do the switching. And some of that's going to be done automatically when you're doing automatic reconfiguration. So so long as you know where the fault is, you can do something about it. And also SCADA will give you other benefits as well, such as like automatic reconfiguration if you've got that SCADA capability. Now, when we look at the DNOs in the UK, they're under Ofgem's jurisdiction, and they've got 3 minutes, and they call it the golden 3 minutes to restore the HV if it goes out. The LV, that I don't know what the requirements are there, and they don't have remote monitoring of LV yet. That's probably going to be the next big investment over the coming years to make the LV network a little bit more manageable and a lot smarter. But the HV network, certainly in England, Scotland and Wales, is very, very much smart. They have RTUs, remote terminal units, on most of their ring main units, and certainly in their primary distribution substations. This is 11 kV, 33 kV and 132 kV. So you can see the map there of the UK with our DNOs. And these RTUs will come in two forms. So this is a secondary distribution RTU. It comes generally in a smallish box. It has got the necessary means to connect into the ring main unit, and this is a physical connection. It will have some form of modem. It might be a radio, it might be a SIM card, or it might be some other means. If it's near to a primary substation, it might actually be hardwired into the primary RTU as well. Now, ring main units typically are self-powered. So that's when we talk about the protection. This is your protection relay, is generally going to be self-powered, and the RTU does not in any way affect the protection. So protection will look after itself. It will need an auxiliary power supply, and it will need a battery inside it, just in case the auxiliary power supply is actually cut. Now, the supply to the ring main unit is for the actuators to remotely open and close the ring switches, and maybe the circuit breaker as well. So you've got full visibility of your status. And you also, modern RTUs are fully cybersecurity compliant. And there's also all sorts of analytics you can do with the information that you can drag back through SCADA, the health of various assets, etc. The I/O there we've got is inputs and outputs, and generally on a secondary distribution substation, you've only got what's inside the ring main unit, the open and close status, trip status, etc. So the I/Os are very, very small, and they're fed through an umbilical into the RTU here. Quite often it will have a padlock on it as well to prevent unauthorized access and then tampering, and usually that's inside a lock substation as well. Now, when we start to look at your primary distribution RTUs, this is a different beast altogether. It doesn't look like the box I've just showed you. It could very much resemble a rack computer with lots of slots in it, and you'll find you're going to have a high number of I/Os monitoring all sorts of stuff, not only inside the switchgear but also inside the substation as well. You'll have high priority telemetry as well, so it may even be, if it's a real high priority substation, it may even have satellite connections, either as backup or as main. So there are different layers of communication philosophies within the utilities, and then the national grid has got their communication philosophy as well. And you generally find that certainly in the UK, other countries may be different, but primary distribution substations are indoor only, so therefore the RTU is going to be an indoor capable RTU. Now, moving on to a closed ring. So our closed ring is slightly different. We don't have an open point, and we've got to change from ring switches to circuit breakers. And this is a significant difference between your open ring and your closed ring, is the equipment. And obviously now the cost has rocketed considerably. So we've gone from, say, £10,000 for a ring main unit. Some of you may be thinking that's a bit expensive, but that's typically what you're going to see in the UK. for a ring main unit, up to something that's going to be in the order of 45,000 for a configuration like that, 3 circuit breakers and the associated protection relays that need to go with each circuit breaker. So we're going to have protection relays which are going to be on our ring circuit breakers, that's there and there. And we're going to have a protection relay on the circuit breaker which is feeding the transformer. And there are going to be problems in this setup I'm showing you here, because when we introduce our faults in the same place, just for consistency with our open ring, we are hopefully going to trip both circuit breakers. Now, I don't know if you noticed there, we've now got one complete loop being fed by 2 circuit breakers, and the load will balance itself out. And this is one of the challenges of network design, is choosing the right equipment for the application. And certainly the amount of current that's going to be fed through that network is going to determine the circuit breaker size in the feeds. But we've also got fault current that is flowing clockwise but also anti-clockwise. So we've got fault current that's traveling in 2 directions. Now, this is going to be one of the problems with this kind of setup is we've got the problem called time grading, but we've also got the problem of which direction the current fault current is actually flowing. Is it flowing clockwise or is it following anti-clockwise? And the protection relay has got to work it out. So and hopefully the 2 circuit breakers bridging the fault will trip, and that's if we've got it set up correctly. Now, this word called time grading, I mentioned it just a couple of minutes ago, is problematic in this kind of setup, because we've got a certain time here. We will need a faster time here, even faster time here, etc. So there's going to be a limit on the number of actual circuit breakers on any one string, for want of a better word. So at some point it's going to become practically it's going to be impossible in a practical sense to actually grade it correctly. If you've only got a couple of circuit breakers or 3 circuit breakers, then that becomes a little bit easier. But when you get maybe 4, 5, or 6, then it becomes nigh on impossible to get the correct time grading to be able for it to all the chain to actually work correctly without spurious or nuisance tripping. So what can we do about it? Well, we can introduce this thing called unit protection. Now, unit protection is a specific type of protection that we would employ in the protection relay. And what we've introduced now is effectively a communications cable. And this is going to be a pilot wire. And this is where another term comes in, pilot wire protection. It's unit protection because it's looking after its own unit. We'll see fault currents outside of it, but it won't do anything about it. So these are now tied together. These protection relays are now tied together by this pilot wire. Now, the pilot wire, you would think would be the best course of action would be follow the main cable, but that's probably not the best solution, because our JCB, if it chops through the main cable, it could possibly chop through the pilot wire as well, or pilot wire only, and then you don't have any protection on your cable. So this is purely cable protection. So fault again in the same place, fault current passes through. Now each of the protection relays outside of the zone are going to see the fault, but they're not going to care 2 hoots about it. It's the way it's set up. They're not going to do anything about it. And then those relays will see it, and then it will trip. So happy days. Now then, in both examples I've just shown you, one of the key things to good network management is monitoring. Now, you can put all the fancy stuff into the substation, you can have the best protection set up, but if you're not monitoring it, then if we get another fault up here, and we haven't monitored it, and we haven't done anything about our original fault around here, then the current will go to this point here, then that one will trip, or maybe that one will trip, and we could ultimately lose not just one substation. In fact, when we've only got that fault there, we haven't lost any supply. We've lost potentially 1, 2, 3, 4 substations, all for the lack of monitoring. Now, monitoring will come in various different forms. So if you've got a SCADA system, you'll have the monitoring already there. You could quite simply have somebody that's going to walk around on a regular basis, i.e. once a day, and just check the status of the circuit breakers. That's another form of monitoring. Or you could put some simple other telemetry system in there where you're going to constantly monitor what's going on with your network. Otherwise, you could take out half your plant or all your plant if you're not careful, and there are recorded cases of that actually happening or in the past, and it will continue to happen as we go along. So one of the best things about this one is you don't need to worry about time grading. All your tripping times will be the same. Right back to your incoming circuit breaker. And sometimes the DNOs will welcome this kind of approach if time grading is going to be an issue, and it takes away the time grading element between the DNO and the main intake substation. So that's just another philosophy that you can take into account. Now, as it says there, another one is differential protection. So if you look at the ANSI code 87 will cover differential protection, and there's one for generators, one for motors, and one for cables. So the L is for line or cables. Now, these are the two typical protection relays that we have come across in the UK. They are ENASS, so they are recognised by the DNOs as a standard form of protection. And one of the downsides with this is you need particular CTs. So the CTs have got to be matched at both ends. That's one of the drawbacks with this kind of system. You've got to have your matched CTs, and the CTs have got to be classic CTs, and that's all in the CT manufacturer's guidance for this type of application, and protection engineers will tell you exactly the same as well. So these are very simple relays, and as you can see, there's nothing fancy about them at all. We've got dip switches there, or we've got dials there, and it's there on the principle that it's like Kirchhoff's law. Whatever goes in goes out, and if there's a mismatch, hey ho, we've got a fault. So that's the principle of operation, and transformer differential is no different. So transformer differential, you measure what goes in, you measure what goes out. Roughly, it's the same. If there's an imbalance, then hey ho, we've got a problem. And this is the same with cable differential or line differential. So if we've got a difference, then it's going to trip both sides to isolate the actual fault. Okay, so there are two types of pilot wire protection in use. You've either got balance voltage or you've got circulating current. Now, the one that I'm going to discuss tonight is balance voltage. That's the typical one that we see here in Schneider going into our switchgear. There is a crossover on the cable, and I'll talk you through how it all works here. So that's the crossover that you want to watch. So you've got CTs at both ends. We have our protection relay, and ultimately the protection relay will trip both circuit breakers. So let's walk through how it all works. So we have our simple scheme here: circuit breakers at both ends, CTs on the cable feeders on both ends, relays, etc. And this is the crossover. So when we get a healthy circuit, 100 amps, we've got CTs of 100 to 5, which will give us a secondary current of 5 amps. So normal healthy circuit. You can see there we've now got the arrows showing you they are going to meet. So in this case, we're not going to get a circulating current because the voltages have opposed, balanced itself out. So we're not going to get current flowing in the loop. So therefore, our relay coils are not going to work. Happy days. Now let's introduce fault current passing through. So we've got 1000 amps there. And now that's fault current in this setup. So when we use the same CTs, we've now increased our secondary current to 50 amps. And guess what? We've still got the same situation we saw before. It's seeing the fault, but it's not going to do anything about it because it wouldn't care two hoots about it. There may actually be standard overcurrent and earth fault protection as well on this scheme, but I'm not showing that. So we don't have circulating current. So what happens when we get the fault inside the actual zone? We're going to get fault current traveling in two directions to the point of the fault, left and right. Now, the one of the CT secondaries is now flipped. So we can see there, instead of it going down the same leg, it's now traveling down in a loop. So all the way around here. So current is flowing, energizing our trip coils. Happy days, the circuit breaker trips, and it trips instantaneously at both sides. Now, like with all things in life, and this is no different, you've got advantages and disadvantages. One of the disadvantages there, you don't typically find it on networks that are higher than 33 kV. They will use different protection schemes on that. We find it quite popular here in the UK on closed rings in this type of protection. Some of the older relays that are on the that are actually installed may not have the supervisory circuits that you'd find in the modern ones. So if you get a break in the pilot wire, then it's not going to go to safe mode, i.e. it's not going to trip both ends. So that's something that to be mindful of. So moving on to what are the comparisons between our different networks. So when we start to look at our radial network, you can now appreciate that, yes, it is possibly the cost effective or the cheapest, as a Yorkshireman would say, it's cheapest. So we don't need to rely on a loop of cable coming back to create a ring. We've got to find where the fault is, and that's going to be done under sanction, etc. And as I showed on my example, whilst we've got 3 substations, 2 of those substations would be out of action until we'd actually repaired the fault and then proved it was safe to re-energize. So that's one. And so you've got to appreciate that there are limitations on the radial. Now, when you start to look at the open ring, you do have to actually allow for time delays in actual supply restoration. So that could be as limit on a private site. It could actually be 2 hours. It could be 4 hours. It could be 6 hours. It may even be longer than that. Particularly if it's not a fully manned site, and you don't have an authorised person that is ready to hand. They've obviously got to get to site for wherever they are, and then they've got to figure out what's been going on. DNOs, they're going to be doing that remotely. They're going to be monitoring it all the time. Their control rooms are manned 24/7, irrespective of weather, irrespective of whether it's a holiday or not. The supply stays on, and they've got them mandated legally to restore it back within 3 minutes. Otherwise, they are going to get fined by the regulator, and those fines could ramp up into millions of pounds. Now, the closed ring, you could already appreciate, is now more expensive. A switchgear is not a ring main unit. It's I would have thought you can never ever find a ring main unit that's got 3 circuit breakers in one common tank. That is highly unusual. Theoretically, it's possible to do it, but in the UK, I've never ever seen one. So it's you've got to use your primary type switchgear. So that's going to be 3 separate cubicles bolted together with a buzz bar on it, and it's going to have to be an indoor substation as well. So it's going to be more expensive. So you've got to accept that. So that's one of the kind of limitations that we've got. Okay, so with closed ring, you won't necessarily see interruption in supply. You may just see the lights dimming and then going bright again, and that would happen very, very quickly whilst the protection relays pick up and then trip, and they will send a trip signal very, very quickly. far quicker than you will get with an IDMT protection relay. Now, a couple of some examples here for you. So this is one I've come across. It's in a circular format, which is highly unusual in what I've seen. They're usually in a layered one, hierarchically. You can see where the open points are. So this we easily will identify. We've got 3 rings in this configuration. We've got generators. We've got a DNO supply, and coming from there, it says East Midlands Electricity, which is the old network, which was Central Networks, which is now part of Western Power Distribution. And then they've got the various substations there. Now we're totally reliant on additional information on this single line diagram. I'm not showing it here. We're showing that the open points are. That could be a link box for all I know, or it could be a ring main unit that is possibly 40 or 50 years old. We don't know. We don't know whether they're going to move these open points around on a regular basis. Some sites will have that as a matter of course, moving the open point down regularly to exercise the switches. The DNOs will move those around operationally as required. Now your next one here, it's again, it's a very different kind of style. We're assuming the crosses here are circuit breakers, but again, there's no legend to tell me what they actually mean. We've no idea what 11, 12, and 13 refer to. It says they're standby set house. No idea what that is. That looks like it's where the supply comes in from somewhere. And we do have an open point there. We have an open point here, and we have an open point here. So are these ring main units, or are they something else? We don't know until we're actually told by somebody who knows and is familiar with the actual network. Another one here I've copied from a customer's drawing, and this is showing me different network configurations. It's a small copy of a much larger site scheme, and the one thing that I am picking out on this one is we have got circuit breakers here, because that very much looks like the ANSI codes. And admittedly, we can't see what the ANSI codes are, but I suspect those are going to be circuit breakers, and it could very well be a closed ring kind of arrangement. So we've got a circuit breaker there by the looks of it. Yeah, I would think that's going to be our a closed ring, and that's the client switches. Now generators, and I promise you I would touch on this at the end of here. Now generators, long been there to supply either backup or more recently, when I say recently, over the last quite a few years, they're used as exporting power onto the grid, i.e. selling the electricity that they're generating. Now, there's been various different guides over the years, and for those of you who know about such things, you'll know the ENA, or Energy Networks Association, have got an engineering guide, and I'll touch on that on the next slide. But in this example here, if you're using it in island mode only, then you've got to take into consideration what blocking schemes are you going to put in place, because we will not want the generator circuit breaker to close until the incoming circuit breaker is opened. So what you can't do with HV switchgear is put physical mechanical rods to prevent one from closing whilst the other one is still closed. So there's literally not those kind of arrangements that you can do. So there's going to be various different ways of achieving this. One of them is by a simple key exchange scheme. So this is going to be like the Castell type key exchange. So where you would actually have an AP that would be authorized to do the tripping of the incoming circuit breaker, removing the key which will have become available when the circuit breaker has been tripped. That will then be taken out. That will prevent the circuit breaker from being closed manually. before, and then putting the key into the generator. It might be going to a key exchange box. Another way would be electrical interlocking, so that the protection relay would be blocked from closing the generator circuit breaker until the incoming supply circuit breaker has been tripped. And that's another way. Or it might be done via your SCADA or whatever control you've got. And another factor to take into consideration is going to be synchronizing. So where you're going to do synchronizing, that's another factor you need to take into account. So are you going to be doing the synchronizing on the protection relay, or is it going to be done at the generator? So either way, you've got to come up with that philosophy as well. Personally, I wouldn't like to start advising which is the best way. I'm not qualified to do that. But that's the kind of sequence that we've got. So just running through that again, we've detected a fault on the incoming supply. It might be that the DNO supply has dropped off. So then our circuit breaker would then trip on undervoltage. It would then send a signal to the generator circuit breaker, right, Fred, you are now ready to close, and then it would then close. Or it may be that if it's got synchronization on it, it would then delay the closing until it's in sync with the what was the DNO supply, and then we may actually have to employ load shedding techniques as well on the site to because the generator may not be man enough to supply the entire site. Right, so final slide before we open up for questions. Generators and this thing called G99. This is a UK thing. There is the European network code for generators. So there's a European guideline as well. And the UK has always had their own guidelines for the UK. And it's agreed with the Energy Networks Association. The Energy Networks Association is the body which represents the DNOs. So each DNO is a member of the ENA. Other companies will be members as well, but by and large, it's DNOs. And they've agreed what the wording is, the technical requirements that are written into this code, etc. So it's called the engineering recommendations. Now, when you are connecting a generator onto the network with the potential to export power, then the DNO will have very strict requirements for the connection, and they will more than likely refer back to the G99, and there is all sorts of commissioning documentation inside the G99 to prove that it will all work, and it does have mandatory protection requirements. The G59, as it used to be, had got things like rate of change of frequency, rate of rise, etc. And they've actually tightened up some of the technical requirements. And it's down to the relay manufacturer to prove that the relay it will meet the requirements technically. So if you need to know what it actually entails, visit the ENA website. And this is one of the engineering documents which is actually freely available. So you don't need to do that. You don't need to pay for the document. So it's there as a free download. So that's. I'm not a member of the ENA. I'm just giving them a bit of promotion. Okay, so what have we covered? Well, we looked at basically what a network is. Then we started to look at the various different ones. So I've got the three common ones there: radial, open, and closed. Then I walked you through some real life examples, for want of a better word, and then I've just finished on generator connections and the UK requirements. The UK requirements by and large are going to be identical to the European requirements as well. Okay, so that's the formal end of the presentation. It's taken just under an hour to run. So I'm now going to stop sharing my screen, and I'm going to hand over to Garda. And fire away, Garda. What questions have we got?
Well, thank you, Nick. We've got about 50 questions, but
whoa,
yeah, we don't have time to answer them all, so I've picked a couple. The first is, when designing a system, how do you determine where the open switch is located in an open ring arrangement?
Right, so it's down to you at the end of the day to decide where that open point is going to be. Typically, you would naturally expect it to be, so you've got both sides of the network, both halves of the ring equally loaded. I would suggest, but you've got to design your network so that both circuit breakers are capable of taking the entire load of the network independently. Okay, so it's going to be down to you and down to where the load, balancing the load is going to be best placed, I would say.
Okay, thank you. And the second one is, on the ring, the breakers are usually zoned by having different operating time delays set. These breakers can be physically miles away. What kind of communication method is used between the breakers to keep the system zoned?
Right, so each circuit breaker will have its own protection relay, which will be then have its a particular setting put in it. Now, if you're talking about closed ring with the unit protection, then each circuit breaker will have its own, it will have an identical time delay on it. So that will be that. Now, if it's an open ring and you've got the feed circuit breaker miles away, which can happen, then it's down to the protection study to determine what the fault levels are going to be and what the time delay is going to be in the feed circuit breaker. So I hope I've answered that one to your satisfaction.
Okay, and we've got a bunch of questions about, oh, sorry, EFPI. So
right.
This is going to be, unfortunately, this is going to be our last one. Basically, so the first point is, how is the EFPI kept powered?
Right, so there is a battery in there, but that's purely for the LED, the indication, and it's the power for the EFPI is self-powered. So it's the core balance CT which will provide the power to the relay for it then to work. And it is an indication only, remember. So its actual power requirements are going to be it's going to be minute, because all it's got to do is power a very, very small relay to trigger the LED, and that will probably be purely electronic net these days. So the power it needs is fed from the CT. Just like an example I can use here is a ring main unit. So your protection relay in your ring main unit is self-powered. It gets the power from the CT, not an external supply. Okay.
Okay. The question keeps going. So can they be monitored by SCADA?
Yes, they can. Provided they are communicating devices, they can be monitored by SCADA.
And finally, does it have directional identification element, i.e. if there is a fault, infet from the substation will be able to distinguish?
The ones I showed, the example I showed you in the photograph, that's a non-directional EFPI. Directional EFPIs are actually being developed because the DNOs in the UK are moving from a DNO to a DSO, which is a distributed system operator. So they're actually having to look at managing their networks in a totally different way to what they're actually they are used to at the moment. So yes, directional EFPIs are coming. The example of the RTU I gave you does have directional EFPI built in it as standard, so we can do it with RTUs, and in a small standalone box, yes, it will be available. I don't know when, because we in Schneider don't make the EFPIs for the UK network, so I can't comment as to what other manufacturers are developing at the moment, but yes, there will be in the future.
Right. Well, we're out of time, I'm afraid.
Okay.
Thanks for the very informative talk.
Thank you very much indeed.
We still, as a token of our gratitude, we still want to give you our IET trophy, which is basically a wine glass.
Thank you.
You're welcome.
I shall be filling it with a glass of red at some point over the weekend.
Well, thank you, Nick, and thanks again. And if anyone would like to know more about how to get involved with IoT, please visit our website or just get in touch with us. Thank you. Well, good night, everyone.
Yep, good night.
Bye.
And thank you, Rich, indeed.
See ya.
Bye.